So I just want to reiterate with the course project, we're learning all these lovely things with textbook examples. Hopefully you guys are finding review of logistic regression and these other kinds of regressions helpful, since they aren't covered in enough depth, I don't feel, in the other classes. One thing that's probably not been something huge in your training thus far statistically is dealing with wild caught data and wrangling it into submission to be able to do all these lovely statistical techniques that you've learned in all your stats classes. So it's a pity we don't have a data wrangling class. I do not know of one that exists anywhere in the world, so we are not alone. But all of you, as you get into working on your course projects, please do not underestimate the amount of time it's going to take to wrangle your data. Even if you think it's clean and well-behaved, you will be surprised at how ill-behaved your data might be when you get down to it. So don't put that off, and get to know your data, get it wrangled and ready, and plan on doing your descriptives if at all possible before I get back, and make notes of the questions you have, whether it's going from long to wide, wide to long, how to create a score out of different items, how to reverse code, how to collapse, any of those types of questions you have. These might not be things you've ever done before. And so part of the course project is getting you to have a real experience with real data. And hopefully all of those complexities, I would love for you to write about that in your paper. So your course project, yes, is about doing multi-level modeling, but it's also about all the other nuances with working with real data that comes about in your career fields. So don't underestimate it, and don't gloss over it in your write-up. When I say things that work and don't work, things that are hard as far as the data wrangling are worth mentioning in the course project. The course project's like a mini dissertation. So it's about more than just the results. It's about the process. And the process of analyzing data is more than just the result you get out. And you should mention those things that were not like textbook perfect or subjective decision points that you had to choose which way you were going to take it. And there's not always one right answer. So it's good to mention the choices you did make and how you did resolve or come to those decisions, even if that's something that gets cut out of a polished manuscript. I would like to see it because it's part of the learning process. And I think it's important for you guys to tell each other about the issues that you're having to deal with, because it's highly likely that everyone is going to come across all of these issues at some point in your career. And it's good to be aware of them and some of the ways we can deal with these really nuancy issues that only come up once here or there. The more exposure you have to real life data, the more well prepared you are for the real data you run into in the future. So I hope that these course projects are beneficial for you in more than just multi-level modeling, in the presentation, in the write-up, in the dealing with raw data. I mean, hopefully it is a real experience that you can draw from that hopefully will help you as you prepare at least to do your dissertation, even if you're not planning to be an analyst in the future and do a lot of this. Does anyone have any questions or concerns about course projects before we move forward? This is your time. Trying to make eye contact with all the little squares. So.
Oh, I had one just logistic question, yeah.
Yeah.
So I'm working with Ariel, we were meeting today, and it looked like the way your announcement went out, and it had those different kind of almost date timelines, which was really helpful. It looked like for the first one on the 12th, just let you know, it's pretty much let you know we have a partner, who it is, and that. And then on the 19th is where we really like give to you the review document and our notes and those types of things. Is that my understanding that correct?
Yeah, so for let me go into student view so it looks like yours, because it doesn't help for you to see the teacher view. So yeah, so that last announcement that I put out about the course project, rubric, dates, and examples. So yeah, so on the 12th, by the 12th, you need to have gone in here, and to submit this exchange, the thing that I need you to submit is just copy, paste, or type your submission right here. A note, all I need is a note telling me who is reviewing your paper and whose paper you are reviewing. So you just need to like, I gave my paper to Carly and I am looking at Julie's or whatever the case is. So that's just so that, like Joey, like you said, so it's just kind of letting me know who's got whose paper. And that's your proof that you actually exchanged it, kind of. It's on your honor. And then go back. No, it's not gonna let me go back.
So to clarify then, we should still send it to them by the 12th.
Yes.
So we don't need to send it to you. We just need to
You
send
don't
it.
need to send it to me. This is between you and your peer. I'm gonna let you guys handle it however you want. Really, you could lie on that and say you gave it to them on the 12th and you didn't, but that's not beneficial to anyone. So when you get it back, I want you to upload, so to submit the return draft assignment, you need to upload some kind of document, PDF or Word, that has the review you did on your peer's paper and not your own paper. So this is like, when you submit a manuscript to be published by any kind of journal, the journal then sends your paper to 3 reviewers. The reviewers read the paper, write reviews, comments, concerns, and send it back to the editor who sends it back to the author. So you're being the reviewers. So you should have some kind of document where you type in your comments and feedback to the author. And I've highlighted in yellow. Feedback should be honest, but it should be kind. We're all in this together. And so we are giving not criticism of the person, but constructive criticism to make the paper better or things that need to be clarified. So it doesn't matter that you're not an expert in the topic that the paper's on. I review a lot of papers where I have no idea what the content is. And, I'm not maybe the best to review the content. You're not here to review the content subject matter. You should be looking, these are the things that you might consider writing about when you're reviewing your peer's paper. Did they include a definition of multi-level modeling and a rationale for why they used it? So this is like a checklist you can use when you're writing your own paper. Did they include enough clarity on the model type? Was it an MLM, a GEE, a GLMM? If it's generalized, what's the distribution and link? Did they use ML and REML? And what optimizers, did they say what software and package they used? Was it cited? The components of modeling. So you can go through this list, and this is kind of a checklist for what you can do to prepare your own manuscript, as well as what you should look for in your peer's manuscript. And mostly you're to read it through and make sure that it makes sense and look for gaps. Michael, did you have a comment?
Yeah, we're not seeing your screen.
Oh, I went to all the trouble to put it in student view and I didn't even share it. Okay, I think I'm sharing the wrong screen. Let me try again. Thank you for letting me know. There we go. Now do you see it? Okay, so this is the return draft to peer review. So this is where you need to submit a file, Word or PDF, where you give the feedback to your peer. And you can just upload the file here. You also need to return it to the person whose paper you read. Obviously, that's the whole point of doing a review. It's giving feedback. And there it is, always honest but kind. So include in this paper whose paper you reviewed and the feedback you could give them. And you can do this in Word with track changes. You could do it on a totally new Word document that you type into. You could photocopy and scan, like if you're old school, you print out your peer's paper and you write on it with a pen and scan it back in. That works. I don't care. You can write this in a RMD and knit it to PDF, whichever format works for you. I don't care about the format. I want you to, look for these things and general flow of the article. Oh, they didn't tell me what BDI means. Where did that come from? What's this abbreviation that's out of nowhere? Because it's brief, there might be things that you think need to be added. Okay. Now that you can see it, does that make a little more sense? Okay, thanks, Michael. So here to submit this one, you have to upload whatever it is with the feedback to the person whose paper you read. Yeah, so here we'll see the announcement now. So yeah, so if you, when you click on the exchange draft, this is where to submit the exchange draft, you just type in here, I gave my paper to so-and-so. You can even say by email or whatever. And then I am reading so-and-so's paper. Click submit. Okay, so I put a lot of different examples. If you take the time to look at a couple of these, you'll see they're very across the board. Not all of these are A papers. Some of them might be B papers. But I wanted you to just see some variety of how other people have done this project in the past. Some are Word documents, some are PDF, some have more or less background, but it just gives you kind of a flavor of what you could do and maybe an example of languaging you could use. All right, we're good on the project. And there's that rubric. Read student view. Okay. All right. Oh, let me go back to student view. I want to see if you guys have the files. Oh, you do? Okay. So today I'm going to start with a PowerPoint. It's been a while since we did a PowerPoint. So in the Files tab under Lectures, we're now on lecture 8/9. And so I'm going to start GEE today. All next week is GEE. And then the Tuesday I get back will also be GEE. We're going to do 2 weeks of GEE. The first half, we're going to do only continuous outcomes. And then we'll move into outcomes that we need to handle logistically that are a yes, no, 2 level, and then into counts and 3 level. That's why we just did the GLMs. So if you want to follow along in the slideshow, there is inside that file folder for lecture 8 GEEs. Here's the combined slideshow for lectures 8 and 9. And again, this is for 2 weeks. And the homework that goes with it, I am tidying up right now so that it's fresh. That will be posted tonight. And I'll send you announcements telling you when this next assignment is ready to go. Somebody emailed me. Who was it? Somebody emailed me and asked me if it was ready to go. Answer is it's not quite ready to go, but it's close. I was hoping to get it done before class. Okay. Can I swap? Okay, how do I get it to?
Might be under display settings.
Swap, there we go. Swap. Okay. I found it. Thanks, Carly. Okay, so these slides are Jameson Fargo slides. Most of the stuff has stayed the same over the last 5 years. GEEs are not new. They are actually newer than multi-level models, but GEEs were kind of published on first by Lang and Zeger back in '86. So, relatively new. They're a lot newer than regular regression or a t-test, but not brand new. So they are an alternative to multi-level and generalized linear models for non-independent or correlated data. So they can handle continuous outcomes, count outcomes, ordinal outcomes, binary outcomes, just like we can do with regular regression and generalized linear regression. But they're not completely considered a multi-level model. And that's why Hawks does not include them in the textbook. So you won't find GEEs in here. There's a couple times he mentions them, but they're not covered in this textbook. So that's why we've kind of paused from reading out of Hawks. I will be putting up the discussion boards for the next 2 weeks for the homework assignments and for the reading/videos for additional material since Hawks doesn't cover the GEEs. So GEE stands for Generalized Estimating Equations. And so they're kind of a lot of times lumped together that they are officially a marginal only model. I think I said that last week. So Multi-level models have multiple levels. They can model the population and the time level. They can do the person level and the class level both simultaneously. GEE only do the averaged over the population. That may or may not be what you want. Here's a good news. For continuous outcomes, they will tell identical stories. For categorical or counts, ordinal binary outcomes, they will tell a slightly different story. So it depends on what your research question is. We'll talk about this more after we see some examples so we can have some context for that. So sometimes they're called different names. We already know people call multi-level models by different names. GEEs are sometimes called logistic regression for correlated data, or Poisson regression for correlated data, or a marginal logistic regression or marginal Poisson. So the key here that's in all of these names is it's either about the marginal, which means averaged over the whole population, or for correlated data. One of those phrases is going to be in the name. So the idea is we have clustered data. Now this can be longitudinal or it can be cross-sectional. It's more often used for longitudinal data. And the assumption is that our responses are correlated within clusters, but the clusters are independent of each other. And this is the same assumption we have with multi-level modeling, that we have, and here's the last one, is we have homogeny and variance in the outcome over time. This can be relaxed a little bit, so it's not mandatory. For missing data, we can deal with a small degree of missing data with these. We can, because we only discard observation if the entire cluster is moving, not if some of the members are missing. So if we're doing longitudinal study where we have a pre, a mid, a post, and a follow-up, we're assuming that those time points are correlated within the same person, but different people are independent of each other. Essentially, we can only do 2 levels like an ANOVA model. And if someone has one observation missing, that's fine as long as all of the observations are not missing. So they can handle some missing data inherently, which is good news. Whereas an ANOVA model has no tolerance for missing data. So I already talked about it being a marginal population average. It is not subject specific. So it models only the mean response over the covariates, not doing random effects. So the models we've done multi-level so far are mixed effects model. They have fixed effects and random effects. This way we do just fixed effects and we handle the correlation not with random effects, but by the introduction of a correlation matrix. A nice thing is we can have covariates are time independent and time varying. So that's a bonus, because in ANOVA, you cannot have time varying covariates. So GEEs kind of fall somewhere between doing a repeated measures ANOVA and doing a full multi-level model as far as complexity and sophistication and ability to handle nuances like missing data and time varying covariates. So the observations can be made at unequal time points, and they can be missing at certain time points. Those are both benefits that ANOVA can't hack. But here's the kicker. The observations should be made at similar time points for all individuals. So if we're doing a pre, mid, post, and follow-up, everyone should have roughly the same structure of observations. Even if they're missing one of them or missing 2 of them, we have the same set of observations for everyone. This would be different than following people, maybe one person we see at the beginning and a month later and a year later and another person we see every 6 weeks. They have to be the same structure of time points, even if they're not having all of the time points or they're not equally spaced. Does someone have a scenario that you wonder if fits or doesn't, or you have an example of repeated observations that we could talk about? Anyone that's working on the memory study or dementia progression grants? I know several of you are.
Yeah, my data will be unequal time intervals.
And why is it unequal? What makes it unequal?
So basically, like, there was one grant in which they were collecting data, and then several waves came out on other grants. So it wasn't planned to be longitudinal at first. So things didn't happen equally. And then some people were, after they got diagnosed with dementia, were out of the first study. And then another study came up later where they were picked back up. So like between time intervals, or between time points, sometimes there's 6 months, sometimes there's a year and a half. It's just kind of all over.
So the dementia progression, everyone has a different number of observations, and sometimes the observations are 2 years apart, and sometimes they're 6 months apart, sometimes they're 8 months apart. It's so vastly different for every person that a GEE would not be a good choice, because there's not that repeated structure of spacing of observations that's the same on all people. Anyone else have repeated measures data? Okay. There are 3 components to fitting a GEE model. Good news is the first 2 are the same as when we do multi-level modeling. We have a conditional expectation of the mean response. This is the link function. And when we have a continuous outcome, I call it normal regression, Gaussian regression, the link is the identity. When we have logistic regression, the link is the logit. When we do Poisson regression, the link is the log. So we still have a link function. If we're doing continuous outcomes, it's usually just the identity, so it's basically nothing. Number 2 is the condition of the variance. This is the fixed effects. So the fixed effects are the same as in any other regression model. Number 3 is new, that we don't use in any other kind of model really. It's a correlation matrix. So that's the new thing we need to learn about. And we had a reading several weeks ago that introduced correlation matrices, and that's what we're gonna go back to right now. I know it's been a little bit of time since you read it, but we have to specify the type of correlation. And so if you have 4 time points, we made a correlation matrix before, that time 1 and 2 are correlated with each other, 2 and 3 are correlated with each other, 3 and 4 are correlated with each other, and those are probably stronger correlations between the correlation between the first and the last. So we have correlation between these repeated measures, and we're going to create one correlation matrix to describe that pattern instead of using random effects to account for the correlation. So there are many, many, many types of correlation structures that have been used by different people in different scenarios. And I'm going to teach you the 4 most common, and that's about it. And the reason is, in real life, with a GEE, you don't have to get this right to get meaningful results. How often are you told that in stats? You can choose wrong and still get the right results. It's not super crucial that you, and I'm going to show you how you actually can compare fit on the different correlation matrices so you can choose the best. But the good news is it's not crucial you get the absolute best correlation structure. So, so side note here, we're going to get into the correlation matrices right here in a second, but the correlation, when we add correlation, you want to be careful not to overcorrect for correlation, and you never want to use both random intercepts and correlation matrix because you'll be repeating the same thing. It's okay to do random intercepts and slopes with an autoregressive 1. We'll get to what that means in a second. Okay. So here are, well, there's 5 on this slide, types of correlation. And I told you we'd do 4, and that's because one of these is the opposite of correlation. This first correlation matrix, what do you see in there? Down the diagonal, we have 1s, and what's off the diagonal? 0. This is telling us all the time points are not correlated with each other. If you choose the identity or the independent correlation structure, you're basically doing regular old regression you learned in 7610. And so it's almost never what you want, but we can do it as a null model to compare the fit of the other 4 correlation structures. So independent, now different, both names, independent and identity, are used in different packages and different frameworks. So those mean the same thing. If we say it's the identity matrix is a matrix that has 1s down the diagonals and 0s everything else. And that is equivalent to saying that observations are all independent of each other. Okay, so then we got all these other ones. I'm going to go over here. Let's see, let me see. I can get a, where's my pen? I want to draw on this slide. Oh, there it is. It fell off. Okay, I'm gonna I have to come over here. Let's see. I want a pen. There we go. I can draw on this. Let's see. Oh, it's over there. If I draw here. Oh, good. Okay, so this one right here is like doing ordinary least squared regression. It just assumes that all the observations are independent of each other. This one over here, exchangeable, what do you notice about the diagonal? The diagonal is 1. It's 1 on all of these. Here, all of these correlations are 0, no correlation. What do you notice about off diagonal here? Compared to each other, all of those off diagonal elements, all of the correlations are
The same.
the same. This is like doing an ANOVA. ANOVA, we have the assumption of sphericity, which is almost the same thing as compound symmetry. Symmetry means the same. All of the correlations between pretest and mid-test, that correlation is the same as the correlation between pretest and final test or 18-month follow-up. All those pairwise correlations are assumed to be equal. So we see off the diagonal on the correlation matrix, they're all the same. Rho stands for correlation. So these are kind of two. So here we have no correlation. That's basically our null model. Compound symmetry is the simplest because we just say yes, instead of saying there's no correlation, we say yes, there's correlation, but it's really simple because we say all the pairwise correlations are the same. The most extreme is this one called unstructured. So we've got 1s down the diagonal. What do you notice about off the diagonal? Check out all those elements.
I guess they mirror each other on each side of the diagonal.
Yeah, you'll always have both sides of the diagonals mirroring each other in any of these. So that's why I only circled the top triangle. I could have circled the bottom. But what do you notice about all these rows inside this triangle?
They're all different.
They're all different. Instead of being all the same, they're all different. This is called unstructured correlation. This is where all the pairs of observations have unique correlations. So those are the most, I guess, extreme kinds of correlation matrices. But there's some pros and cons to both of these. So we've done ANOVA before. ANOVA has sphericity. How often is sphericity true in real life human subjects? It's never true. It's always too much of an oversimplification. So the exchangeable compound symmetry, although it's simplest, it's almost always violated. Unstructured is never going to be violated. It lets all the correlations be unique. The problem is that's how many different correlations, instead of having it all be the same single correlation, how many different correlations do we have here? Row 1, row 2, row 3, there's 6 of them. So you've got to estimate 6 correlations. And this is if we have 4 time points, because we have 4 rows by 4 columns, it's 4 by 4. What if you have 10 observations? How big is this matrix going to be? It'll be 10 by 10. How many different correlations does that make? A lot. So exchangeable is never violated, but sometimes it's overly complex for the situation. So there have been several different alternatives that have been developed over time that are somewhere in between the way too simplified compound symmetry approach and the way too complex of unstructured. And down on the bottom, we have 2 of those options. So I'm going to look at this first one down here in the lower right-hand corner. So we got ones on the diagonal. Then what do we notice? Off this diagonal, all of these are row. So this is between 1 and 2, between 2 and 3, between 3 and 4. So adjacent time points that are right next to each other, have the same correlation. And then the second moving up the diagonal, these are row squares. So this is between first and third, second and fourth, and if we had it, third and fifth. So these are alternating. So they're separated by 1, is row squared. And then if we move further, it's row cubed. Now let's think, what is a number that row could be? What does row stand for? What's row?
The correlation.
Correlation. So what's a possible number that it could be?
Oh, I guess between -1 and 1.
-1 and +1. So let's say they're positively correlated. So what's a number?
0.7.
0.7. So that's row. What's going to be row squared? 0.7 times 0.7 is
0.49.
0.49. What's row cubed?
Get out my calculator.
Calculator. Carly, you typing it?
Yeah, hold on a second.
The downward eyes gave me hope.
It is 0.24. Oh, no, cubed. Hold
Yeah.
on a second. Oh, gosh. Okay. That seemed
That
right.
actually
It
sounds.
is 0.10. Nope. Typed it in wrong again. 0.11. I swear it's that. No.
What about if correlation's a number between, we're going to say 0 and 1 and ignore the negative. If it's between 0 and
0.34. I'm so sorry. My brain's not working.
0.34,
Yeah.
you're on the spot. I know the feeling. So if a number is between 0 and 1, if we make it a higher power, what happens to the square and the cube and the quad? It starts to get smaller and smaller. I think that on an earlier assignment, didn't we have repeated observations and we made the correlation matrix and we saw that time points that were close together had a stronger correlation as the length of time between time points gets further apart, the correlation becomes weaker. It's this correlation decay. That's what autoregressive tries to get at. Now, here we had 4 observations. How many different rows are there? Row, the Greek letter row. There's not 3 rows. There's only 1 value for row because we end up squaring it and cubing it. So there's only 1 row value. So it's as simple as the compound symmetry, but it more closely matches what we usually see in real life. So this autoregressive is usually a biggie for repeated time points on human subjects. It ends up showing that decay of correlation over time. Now, this one over here is called a toplets. It's similar. We still have ones down the diagonal, and here we have row with a 1 and row with a 2. But what do we notice about the row with a 1? Where's the 1? It's not a power, it's a subscript. Instead of being row squared, it's row, the second value. So this one actually has 2 values, whereas this one only had 1 value. And often we do what's called a banded toplets, and we say eventually it's close enough, we're going to call the rest of it 0. So it's about the pattern of correlation between repeated observations. That is a giant mess. Okay. So let's talk about in detail a little bit more about each of these correlation structures. And I need to set the alarm. I didn't do that. Who's my reminder person? My brain didn't remember. Should we go till, what time should we go till? 5:20? That's almost now. That's a good time. Okay. 10 more minutes till break. Okay. The independence assumption. It assumes there is constant variance over time and there is no correlation. There's only one parameter, the variance. It's what's assumed in regular ANOVA, not repeated measures ANOVA, regular ANOVA or regular regression. It's very rarely, never appropriate in longitudinal analysis. We use it to compare other structures too. Here's our unstructured. It's the opposite of independent. It says that there is correlation and every pairing has a different strength correlation, but it ends up with you can do this with down the diagonal, different variances. So this is the opposite of homogeny of variance. So we'd have a different variance at each time point plus a different covariance or correlation between all repeated measures. So it sounds like a good choice because it's guaranteed to fit the data. The problem is it usually sucks up all the power if you have a lot of time points. So as the number of time points goes up, the number of things that are in that matrix goes up. So it's only usually recommended for when you have a large sample of balanced data and a small number of repeated measurements. So that's the last bullet on this slide. If you have a small sample or unbalanced data or lots like 10 time points, this is a no-go. Okay. Compound symmetry, woo, woo, woo. It's what repeated measures ANOVA does. And it's simple because we have one variance, because we have homogeny of variance and one correlation, that's sphericity or compound symmetry. But it's probably not appropriate if we have decreasing or decaying correlation over time, or sometimes the variance changes over time. So we've already seen with repeated measures ANOVA, homogeny of variance and sphericity or compound symmetry are often violated. Okay, so here's the toplets. It assumes that any pair of observations, if they're spaced the same, like every adjacent time point, they have the same amount of correlation. This is a good option if you have structured time, but not if there's unstructured time between your measurements. So if your measurements, especially if they're largely equal, like every 6 months or every 2 weeks, this is a good option. Toplets is. Autoregressive, and often it's called autoregressive 1 because the power goes up by 1 each time you move further apart. So it allows for decaying correlation. It allows for correlation between the observations. And sometimes you can change the lag so that earlier time points are more correlated than further apart or later time points. So this is a good one to know about for human subject repeated measures. So banded just means at some point, observations are so far apart in time, there is no more correlation. So if I'm looking at depression, how depressed a person is, if I'm doing measurements every 2 weeks, those are likely to be correlated. My depression today is probably pretty close or closely related to my depression in 2 weeks. But what if I'm measuring depression every 10 years? That might be so low of a correlation, we can assume that it's not correlated. And so that's why in banded models, after a certain point, we set the correlation to essentially 0. We're not saying that it is 0, it's just close enough we can treat it if it's 0. Knowing if you should do a banded model depends on the situation you're studying, and it's very content specific. Usually we don't worry about banding unless we have lots of time points. So there are some other ones that I'm not going to get into a lot of depth, especially not on the homework, but you need to be aware of because you might read about them somewhere. There is one called the autoregressive moving average. So that's the ARMA 1-1. So autoregressive means that the further apart in time, the less correlated, and the moving average part has to do, let's see, with a multiple. That's the gammas that are here. So at the bottom of the slide, it says there's a drop off in correlation from one point to the next, that the drop off is really high, but the further drop off is higher, at higher lags is small. So we have this varying drop off. It's really hard to make the case for this one unless you have a lot of research done on the exact thing you're measuring in the exact subpopulation. And in reality, the GEE model doesn't perform that much better if you go to this much detail. So that's the reason I'm not going to really focus on it a lot. So there are all different versions of the autoregressive and lots of special cases of toplets. You can do different decays and lags, but in general, you don't see them a tremendous amount. They were really all the rage for a while, but it turned out they didn't make that much difference. So knowing about autoregressive and toplets along with independence and compound symmetry is probably as much as you really will use. It's all that anyone really uses anymore. So another problem we can run into is non-constant variance. And there are some models that handle that. The other option is we can transform our data. I'm not a huge fan of transforming data to make it more normal and less skewed. Has problems with the standard errors, but sometimes it can help a little bit. If we do unstructured, it naturally has the changing variance built into it. So if you have a few time points, like 3 or 4, even up to 5 time points, unstructured might be a good way to go because it handles the heterogeneity and variance. Random intercepts and slopes, that's what this RIAS, it naturally handles that as well. So, okay, restricted, okay. So all of these covariance patterns in principle can be extended to random or unequally spaced time points, but they don't work really well. So if you are in a situation like Julie, where you have, Julie, that you have, anytime you have unequally spaced and unstructured and everyone has their different visit or measurement scheme, Julie, it was Julie, that Julie, not this Julie. Struggle. If you have that different timing for every person, unstructured, any of this GEE is probably not the best choice. It's probably better to do a full-blown mixed effects multi-level model. GEEs are really the most beneficial when you have very clear measurement structure that everyone has approximately the same timing of visits as each other, even if they're not 1 and 2, time 1 and 2 are a different spacing as 3 and 4, but everyone has roughly those same time points. And most planned randomized trials do endeavor to do that. Okay. So strengths and weakness. Although allowing for the correct correlation, like I said, getting the best correlation to fit your data is important, it's not totally crucial.
Can I ask a quick question? All those different, like those matrices you just went through, all those different types, is that like some sort of a decision you make in this GEE process, like which one of those like you use, or I guess I don't understand that in the process of doing a GEE.
Yep, we're going to look at an example after we have our little break, okay?
Oh.
And so like most things statistical, if you're not sure, you can fit all of these and then do a comparison on the fit. You cannot do the ANOVA likelihood ratio test, but there, I'm going to show you there's at least 2 ways that you can judge which one's the best.
Okay, so this is the thing you were talking about. Now I remember when you said you can't necessarily maybe get it wrong because you could fix it. So you do make a choice, like in the when you're typing in code at some point, you have to like select one of these to implement.
Yes. Yes.
Okay.
Yeah.
But why would we select one of these over a mixed effects model?
That's a good question. And one we will talk about when we come back. How's that?
Cliffhanger.
Cliffhanger, don't forget to come back.
Did you know, sorry, this didn't go on the recording, but just a fun little fact with Zoom. I found something and you can give yourself like eyebrows and lipstick and facial hair. It's weird.
Facial hair, that might
Yes, it's weird. It's weird. I was showing Allison the other day. I was just amazed by it.
Everyone's going to be putting on facial hair while we're doing the lecture.
So they have all these like shades of lipstick too. It's amazing. I'm like, interesting.
Does it make you look like less bags under the eyes?
No, it doesn't do anything like that. You just like, it's just the eyebrows and the lipstick and the facial hair. You just have like
that's what I could use.
Yeah.
Okay, I want to go to the example on the encyclopedia to give us something to anchor these new ideas to. So I'm in the volume 5 multi-level modeling. We've done the MLMs. Now we're getting to the GEE. So right now this is chapter 14. This could change in the future, but it's the GEE continuous outcome. Then next week we're going to do binary and count outcomes. So here we go. This is a data set you've seen before. It's the blues. I think we did this on our first review regression and homework. So I just want to show you the packages. We have a lot of the packages we've seen before. Tidyverse, Pander makes tables, furniture, TechReg, and Psych. So those are just regular packages. I'm loading the LME4 package and probably should load the lemur test because I'm going to compare this to a multi-level model, the GEE. And I've got the core plot package that makes that nice correlation matrix plot with the circles and yummy. These are the new packages you're going to need. And I think these came with our download at the first of the semester. There are 2 packages that solve GEE, general estimating equations. So someone said, why would you do one of these when you could do a mixed effects model? And the answer is you usually should use a mixed effects model. But I will tell you, sometimes these fail to converge, especially if you have dichotomous outcomes. Multi-level logistic regression can be a bear. My new abbreviation is PITA. Somebody put that in an email today, right, Julie? I was like, PITA, what's PITA? P-I-T-A. And it was in the reference to data wrangling, pain in the patootie. So, logistic multi-level models with mixed effects can be a pain. So GEE are a nice alternative if you're having major failure to converge. Also, mixed effects regression, when they first came out, were they sucked the computer's brain power. You had to have a really, really powerful computer to get them to run, which most people didn't have back 20 years ago, 30 years ago. GEE take a lot less computer power, and so they caught on really fast before. You still see them used, but they're definitely less in the middle, in the new, because yes, if you can do a mixed effects model, that's what you should do. But if you can't do a mixed effects model, a GEE is better than doing a repeated measures ANOVA. So it's kind of in between. So there is not one great package I've ever found for GEE. There are these 2 that both have pros and cons. One's called GEE, that's it. The other one's called GEE Pack. And one of them fits the model in a way that you can put it in a TechReg package. The other one fits it in a way that you can do plots and compare models. So it has to do with how the output is put out of these models. They get the same estimates, but they format the output differently. And so I use both of them, and I'm going to teach you how to use both of them because you do what works, and this is what works. There is this third package. It's for multi-level models, and it is for inference. Multi-level model inference is what it's an abbreviation for. It has a function in it called QIC, and this is the best way to compare models, to compare GEE models. So those are our new models. Now, the last one here, this is the handbook for statistical analysis using R. This is a package that we need just to get the data set. So to remind you about the Beat the Blues data set from way back when, we have a treatment and a control group. There's the treatment as usual, TAU, which are doing treatment as usual. I don't know what that means. And then the Beat the Blues group, and they're doing the Beat the Blues program. And we're trying to see if this changes depression over time. Depression's measured with the Beck depression inventory before treatment, and then at 2, 4, 6, and 8 months. Notice everybody has the same structure of observations. Everyone's at 2, the second month, 4, 6, 8. Now, someone could be missing one of those, but it's the same set structure every 2 months for every person. That we also gleaned if the person was taking antidepressant drugs, yes or no, just yes or no, and how long their current depressive episode was when they start the study. So when they started the study, an inclusion criteria is they had to be depressed, and they asked them, have you been depressed for more or less than 6 months? And so that's our variable to measure severity, kind of at baseline. So here's our data set. So the first person was not taking an antidepressant, but had been depressed for more than 6 months. They got put in the treatment as usual group, and their depression scores went 29, 2, 2, dropped out. What would happen to this person if we did a repeated measures ANOVA?
They'd be removed, deleted.
They'd be removed. Here's the second person. Yes, they're taking the antidepressant. They've been depressed for a long time. They got put in the Beat the Blues, and their scores, depression went 32, 16, 24, 17, 20, and so on. So you will see, check out this person 97. They were taking antidepressant, but they'd only been depressed less than 6 months. They were put in the treatment as usual. They had a score of 28 at the beginning, and then what? Bye-bye. They never came back. Does this sound familiar? Those of you who have been involved in human subject research. This is what happens, gosh darn it. So I tidied up the data set. Let's see, I updated this and I just pushed the changes. Let's see, did the changes come through? Yeah, don't think so. Okay, so here is a person profile plot. A person profile plot is also called a spaghetti plot. It's the raw observed data with the points for all the observations connecting the dots. So I have only plotted the depression at 2, 4, 6, and 8 months. The pre-score we're going to use as a covariate, not as an actual time point. That is another decision for another day. So I've separated out my hairball into 2 groups. Eyeballing it, treatment as usual versus Beat the Blue. Can you eyeball any trend here? I put a smoother line on both. Does the program work? Yes, no. Can you tell?
Well, the
No.
Beat the Blues seems to finish with lower depression, but they also maybe started with lower depression. So you'd have to compare the slopes, and it's a bit hard. Just
Hard to compare them when they're side by side, yes. But Carter's picked up a good thing. The Beat the Blue ends lower, but it also started lower. So we need to see. Here I've split out not just by treatment group, but I've also split it by if they were taking an antidepressant. Now, treatment as usual, beat the blue, that was randomly assigned, but taking an antidepressant was just whatever they came with. So that was an observed variable that we need to control for. Again, hard to tell here because they're on different panels. So here I even did it even more. Within each panel, I also colored the lines by if they had been depressed for a longer than 6 months or less, if it was a more recent short-term depression that they had when they started. Is there something going on? It's worth looking at. How about we say that? Okay, so here is, I've taken my data set. Now the long format is what you need for modeling and plotting. The wide format is what you need for descriptives and correlation. So both formats come in handy. So I'm plotting time on the x-axis, depression on the y-axis, and I'm going to group it, color and filling in by treatment. So just by treatment. And when I put geom smooth, it's going to fit a linear model to both treatment groups. There, so there's both treatment groups on the same plot instead of different panels. What do you think? Is the program beneficial? Or more importantly, is it more beneficial than treatment as usual?
Can't tell.
Can't tell. Are the slopes the same or different?
Looks the same.
They look the same. So it's like Carter pointed out before, the beat the blues end lower, but they started lower. So it looks like the change over time, the slope is roughly the same. Now we don't have a p-value yet. We need a model for that. But visually, I would say that program's not that much more beneficial than the treatment as usual. If I have depression, I'm going to go down the same amount no matter which group I get put in, is what it feels like right now. Feelings. Okay, so here is how we do correlation. Core is in the stats package, which is base R. So it gives us this beautiful correlation matrix, which do you like looking at that correlation matrix? It's a lot of numbers. So we can use the core plot.mixed to make a picture. Okay, looking at this picture, this is the correlation matrix we use to determine what correlation structure we should use in our GEE matrix. Unstructured would be that all of these correlations were 0. Are they all 0? They're not 0. Compound symmetry would say that all the correlations are the same number. Are they all the same? No, so both of those are not. Now, independence would say all of these are unique. Are they all unique? They're all different. They're pretty different. But is there an overall pattern to which we can simplify this? Let's look along the diagonals. So one place off the diagonal, these correlations are the strongest. The correlations are generally about 0.7, 0.8. We go 2 off the diagonal. These correlations are now slightly smaller. If we go further off the diagonal, we get weaker and weaker. This is kind of that autoregressive pattern. So is it clearly one or the other? It's never going to be identical to any of those. No correlations, not right. All of it unstructured with all different correlations will definitely fit the data, but it might be overly complex. So we're going to try all 4 of those to get a better idea. Now, before that, in the encyclopedia, I've quickly gone about this the wrong way. So first I did ordinary least squared regression. So ignoring the fact that they're repeated measures and treating every person's 5 observations as if they were 5 different people. And I'm putting in here as my covariates the baseline severity, the length of the current episode, whether or not they're on an antidepressant, the treatment group, and then time. So I put them all in there, and then I'm looking at interactions. And I made a tech reg table. It's actually knit reg in the new version when it gets updated. So here's our tables. All of these interactions end up being non-significant. So here is the plot of my model. So this is ordinary least squared regression with the LM command, assuming independence of the repeated measures. It looks like that spaghetti plot smoother before. Okay, so this is basically the same thing. So when we did the scatter plots here and I smoothed it, I get the same thing as if I just did regular regression. Looks like there's nothing going on. Okay, now we're going to do it as a mixed effects regression, a multi-level model. So this is what we've been doing. We're using lemur test, LMER. I'm putting in all of my variables. What kind of multi-level model, what random effects do I have in this first model? Random what?
Slope?
This one's not random slopes. This one is random
Random nothing?
intercepts. The number one means intercepts.
That's
The second model has random intercepts and slopes because we have the word month there and it's inherent that there's the one unless we said otherwise. Okay, so here I've put it in a single table. I'm gonna make this smaller so it'll all fit on the screen. I've got ordinary least squares, which pretends like the observations are independent, random intercepts and slopes. Look for all of those. For which one of those is treatment as usual versus B to B significant? Do they all tell the same story? No. In the ordinary least squared, it says treatment as usual gets 2 stars, the wall test says it's significant. If I do a multi-level model with random intercepts or random intercepts and slopes, it says the treatment is not significant. Let's see, residual variance. Which one would you think is better just based on residual variance? Random intercepts that's in the middle or random intercepts and slopes, which is on the far right?
Random intercepts and slopes.
The slope, intercepts and slopes seems to reduce residual variance the best. Okay, and we can do likelihood ratio test and it tells us, oh, what does it tell us? Julie's shaking her head no. Random intercepts and slopes does not, the extra complication is not worth it. So even though it reduces residual variance, random intercepts is probably the better model for this data.
That's because that's not significant. There'd be a little star by that 0.6.
Yep. So here I'm plotting the random intercepts model. Check it out. Does this look the same as the previous plot?
It looks like the confidence intervals overlap on this one. And
yeah, check out those confidence intervals this time. The lines themselves are not that different, but what happened to our confidence intervals? They got a lot bigger, and that's why it's not statistically significant. This is an exact illustration of what we read about in Hawkes chapter 1. Hawkes chapter 1 says, if we don't take into consideration the correlation, we will underestimate the standard errors and inflate our type 1 error rate. When we treat the observations as if they're independent, we get this really small standard error. When we acknowledge the correlation, we get more appropriate standard errors, which happen to be wider. Okay, so that so far is a review of everything we've done. Are you ready for the GEE? We got 15 minutes. Can you hang in there for 15 minutes? Okay, ask your questions because I don't want to leave you high and dry. I'm really worried about next week. If we have to redo it, we'll redo it, but give it your best shot. Okay, GEEs. Here is the code to fit a GEE model. Hang on to your hats. We're using the GEE package, the GEE function. Surprise. Okay. The first thing we put in is the formula. Check out that formula. The outcome is BDI and our predictors are, whoa, this looks like every other formula we've ever written in R, right? Okay, what comes next? Data equals the name of the data set. Is anyone lost yet? Good news. Okay, there is some new stuff here. Notice at the end of the formula, we do not have the parentheses with the one vertical bar ID. So instead you have to say what ID is here. The ID is the identifying variable for which observations are grouped together. That's new. Now, you have to put in which family. Now, if we have a continuous outcome and there's no link function, use the default to normal regression, you say family equals Gaussian. If you forget that, you can come back to the encyclopedia and check it out. The last thing, the new thing we have to add in here is the correlation structure. So the first model I'm going to run is independence. That's treating the observations if they're independent. It's our starting model. It's not the best model. I can guarantee it's not the best model. It never is, but we're going to start with independence. Okay, how does that code feel? Okay, we got GEE package, GEE function. Really hard to forget that to run a GEE model. Formula is the same way, but we have no random effects at the end. Data is the same way. You have to add the ID equals a variable name because we don't have the parentheses at the end of the formula. We have to add the family, which for today is always going to be Gaussian. Next week, we're going to change it to like binomial with a link equals logit to do logistic regression, or Poisson with a link equals log to do count data. And the newest thing is that correlation structure. Now, the way it fits, the computer goes about fitting the model with the GEE package is it first fits it as if with regular regression, and then it does an iterative process. It is always going to spit out the normal regression that it starts with. I cannot figure out a way to stop it from spitting this out. Usually when we save in the code chunk, nothing is spit out as output, but it just does this. I can't get away with not. Okay, so this is the independence model. Bad model, something to start with. Check out this model. What did I change?
Correlation structure.
The correlation structure is now exchangeable. That's the compound symmetry. You say exchangeable to do compound symmetry. Now, I'll point out the names. I'm calling this Beat the Blues, GEE, IN for independence. I'm calling this one B the B, GEE, EX for exchangeable. Guess what I'm going to do next? Anyone guess?
Autoregression.
I tried autoregression. Now, autoregressive has, you have to put two things. You put core struct equals, and in quotes, AR-1. That means autoregressive moving. And then the MV, you have to say moving what? And it's the number 1 for autoregressive 1. In this case, I've commented it out because it failed to run, because there is at least one person that has only one observation. If you have any people in your sample that only have one observation, this package croaks. The way the package is written, it will just croak. So I just commented out the autoregressive for this example. And the last one I did is unstructured. Okay, so really I've only done 3 of the 4. I didn't do toplets, because toplets with this many observations, toplets and autoregressive are basically the same. Okay, if you ask for a summary of one of those models, you'll get a heck of a lot of output. You'll get told that it's a GEE for dependent model, dependent data, and that it's based on the S function from 1998. S is a computer language, it's just information. And we're doing the identity link Gaussian distribution. This just means we're doing regular old regression, and we chose independent structure because this is the model I named IN. So it gives you basically what the model is, and the call is what you typed in. Gives you some summary on the residuals. Ouch. What do you think about these residuals going from negative 24 to 27? They're supposed to be z-scores. What do you think about z-scores that size? Yeah, well, we'll ignore it. Okay. So your coefficients are coefficients like you get in any regression. These are our fixed effects. We get estimates, and it says a naive standard error and a naive z-score, and then it says a robust standard error and a robust z-score. The naive one ignores the correlation. The robust includes the correlation. Which one do you think is more correct? Just based on the name.
Robust.
Robust. Use the robust. So, and then it gives you the scale parameter, which we're going to ignore for the time being. And this only took one iteration. This computer program's so good, it just had to do one iteration and it was done. And it gives you the working correlation. What do you notice about that correlation structure? Does it look familiar?
Matrix.
That's the independence. It's basically doing regular old regression because it's the independent model. It will have the independent correlation structure. Okay. Now here, this I did summary, but now it's the model EX. EX was for exchangeable. Now we get, oh, look at our standard errors. Did they get any better? Well, they're at least, or the residuals are now more symmetrical, but yeah. We get our coefficients still, a scale parameter. This one took 5 iterations. So the first time it does independence and then updates it and it had to do it 5 cycles basically. Check out this working correlation matrix. What does it look like? One's down the diagonal and what's off the diagonal? All pairings are exchangeable or the same, so they all have the same correlation. What's rho in this case? Rho is 0.69. Okay. Now here, this one says unstructured. What do you think? Is it going to take 1 iteration, 5, between 1 and 5, or more than 5? 10, Mike says. Anyone else have an estimate? A lot? Let's see. Okay, so this is the unstructured one. Check out how many iterations. Only 5. Wow, that was pretty good. What do you notice about the correlation structure with unstructured? All of those numbers that are not 1, all of those numbers are, looking at 1/2 of it anyway, they're all different. That's unstructured. Okay, so I did a TechReg or a NitReg package. So I put in the ordinary least squared, the random intercepts, and those 3 GEE models. Okay, let's look at treatment. Which ones are similar? Which ones are to each other? Which ones are different?
The independent looks like the ordinary least squares.
Independence will always be the same as ordinary least squared. Independence is basically doing ordinary least squares. So we can think of it as an ordinary least squared. What about the exchangeable and the unstructured? Compared to the random intercepts?
They're all pretty similar.
They're all pretty similar. If you compare them, this is where I said you can guess the wrong correlation structure as long as you have close to the right correlation structure. Exchangeable and unstructured actually end up giving us almost exactly the same model. That's pretty good. Okay, now these models I fit with what package? GEE package goes nice in the TechReg table. We like that. The problem is they're impossible to plot. And the best way to interpret your model is plot it. So we're going to go with that second package to wrap up today. This is the GEE-GLM package, or the GEE-PAC package, and the command is GEE-GLM. And what it does is it packages the output for as the same way that GLM does, so it's easier to plot. Again, the answers will be almost exactly the same between these two packages. The GEE package goes into TechReg tables better. The GEE-PAC, GEE-GLM, that is easier to plot. So I'm going to redo the same models. Now let's check out the syntax. Formula, that's the same. Data equals, that's the same. ID equals, that's the same. We have this new thing though, it's called wave. We have to tell it which variable is the wave, which is like month 2, 4, 6, 8. And it does that to keep track of missing data if someone skips a wave, like it skips a measurement time. So this is like our time variable. Wave is our time variable so that it knows how to line them up if someone's missing data. And you can't skip that step here. Family equals Gaussian, and then core struct. Now, the core struct is slightly different, the correlation structure. Independence and exchangeable are the same, but autoregressive is a little different. So you want to refer back to this code so you know how you type it in. Now this time, autoregressive 1 does run. This package is put together so it will run. So basically, I'm running the independent, which is ordinary least squares equivalent, and then exchangeable, autoregressive, and unstructured, all 3 variations of the correlation structure. The nice thing about this is then we can compare the models and plot the models. Again, the numbers will be almost exactly the same. It's the way that it's put together underneath the hood. We cannot use the likelihood ratio test. GEEs are not a maximum likelihood. It does not maximum likelihood. It does this iterative process. So there is no likelihood. So if you try to do the ANOVA command for the models, it will tell you the models are identical because they only differ on the correlation structure. And your answer will be no, no, no. You cannot do that. Here are some references if you want to read more about it, or you can take my word for it. Since there is no likelihood, in the standard way, we can't even calculate an AIC or a BIC because those are based on the likelihood. So some really smart people, and these smart papers show you, came up with an alternative model fit statistic. And it's a quasi AIC measure, so they call it QIC. The good news is this is really easy to do. QIC is the command out of that multi-level inference package. So you say QIC, give it the list of names. Now you do have to tell it if you want type R or not. So, because there's different versions of the QIC. So here I put some notes because I always have to come back and read this because I forget. QICI is based on the independence model. And that's what Pan in this first article in biometrics said was an asymptotic unbiased estimator. So it's useful to choose the correlation. If you're choosing the correlation structure, you're trying to decide which correlation structure you should use. You should choose the model that has the smallest QICI. That's versus the QICR. So you just say type R equals false. And then you get a little, so we want the smallest QIC. Which one has the smallest QIC in this case?
Exchangeable.
4.
Exchangeable is the lowest, but look how close unstructured is. There's a couple that are really close, but exchangeable wins the correlation structure battle. Now this is QICI is for choosing the correlation structure. If you're comparing models that have different fixed factors for different predictors, then you want to use QICR, type R equals true. If we were going to choose the variables that are in our model, but so in this case, we do not want to use this because this is all of these have different correlation structures. If these models instead had different predictors in them, then I would do it this way. Now, if you don't say this type R, true, false, or wait, you say QICU, that gives you another kind of QIC, and it's approximately the same. And this one can be useful, again, for variable selection, but not for selecting the correlation structure. So you have to be careful of that. There is a nice, fun command called model cell. This is for model select. And it will sort to the top the best model. So when it sorts these model, because we said rank equals QIC, so rank them or sort them by QIC, which model comes to the top? That exchangeable. That saves you the trouble of having to look down the list of numbers to find the smallest number. Just nice. Okay. So plotting the model. Okay, so this hasn't updated here. So let me go back. It's not gonna. Keep no. Okay. Let me go into R and I'll show you this as we wrap up. Oh, that's the homework. We don't want to show you the homework yet. Okay. Last thing of the day. Okay. No, no, no. I closed it down to post it. No, deep blue. Okay, so. Okay, I found today that this new package, Interact Plot, works with GEE models. I was so stoked because these used to be the biggest pain in the PETA to plot. So now we can use this interaction package, Interact Plot. We tell it the model. I'm going to plot the exchangeable with the GEE GLM version. The predictor is on the x-axis and the moderator is the different line types. And check it out. It plots so pretty. But just to show you, this is how I used to, this is the best way I used to know to plot these things. It's kind of ugly. But I want us to look at this. Here is the plot of all of the different models. I want you to look how different these are. The unstructured, the autoregressive, the compound symmetry, and the independence. Do they look substantially different? They don't, because the parameter estimates will be largely the same. The standard errors will be different. So you want to choose the one that's the best fit to get the more truthful p-values. Now here they're on different panels, and we've already seen judging sameness on different panels is hard. So here I made a plot where I threw them all on the same panel, and they're different colors for the different ones. Now can you see how are they exactly the same? Now which one did we find which fit the best? What was it called?
Compound symmetry.
It was exchangeable, which is the same thing as compound symmetry. So that's the dark blue one here. Can you see how the other ones are close to, but not the same? Which was the worst one to choose? The one that we know is wrong.
Independence is like the OLS.
The independence, that's like OLS. That's the green line here. This green. So that one is probably the furthest off the other ones, but comparing other than independence, the other three are very, very similar to each other. And this is why in real life, as long as we choose a close to accurate correlation structure, we're okay, because even if it's not the perfect correlation structure, it usually will get us close enough to the right answer that it works. Okay, I went forward and I tried interaction. There's no interactions. So it turns out the only thing that's significant in this case, what did we see? Where's our GEE? What's the only thing that's significant?
Time.
Time, that month variable, that's significant. And our severity at baseline. Does length have any effect? No. Does drug have an effect? No. Does the treatment have an effect? No.
But the drug does in the independent.
In the independent it does, but should we trust the independent model?
I guess no.
Why not? Are repeated observations independent of each other? They're not. Ever. Okay. That's your introduction to GEE models. If you're feeling a little bit overwhelmed, that's okay, because it's day one. We're going to have 2 weeks to get these covered, okay? I will leave you instructions on Canvas in an announcement when the next homeworks are ready to go, when the discussion boards are ready to go, when the videos and instructions for next week are ready to go. Look for those definitely within the next 48 hours. Right now you have a homework assignment to finish up. If you hit any snags, use that discussion board or email me directly. I've got my list of emails to write. You guys are my focus for the next 24 hours. Okay. I'll stick around a little longer if you have questions on the homework or anything else.
Have a good trip.
Oh, I hope so. Here for healthy.